Tierra, can you hear me yet? Can you hear me? Okay. Dion, you hear me? Okay. Oh, there's Deborah. Okay, good. And all we got's Alexis to go here. All right. Guys, I pulled something up on my computer I wanted to remind you about. What am I looking at there? Is that, oh, that's Dion's desk, I guess. I don't see Dion at it, but there's her desk. Okay. So I pulled up that integral guide sheet that I talked to you about yesterday. And it's a good, it really is a good thing to look at and say, can I do this? Can I do that? Is there, so if you hadn't looked at it, go ahead and look at it, because it'll be a resource for you when you start taking your test. Now, let me, Alexis, can you hear me yet?
Yeah, I can hear you.
Okay, good. All right, good. This next test is going to be integrals plus 2 more sections. And the 2 sections that I'm going to do have nothing to do with integrals, and they're easier, which is good. So that's what I want to do right now. I want to give you a break, sort of, and I want to talk about that today and tomorrow, and we'll be finished probably tomorrow with what I want to have on the next test. And we'll talk about when's the best time for you to take it after we come back on Monday. Okay. So, and what I do today is not going to have, it's not going to take, I don't think, the whole period. So I'll save some time for more questions on integrals. I hope yesterday, download. All right, sure, I want to call it. All right, so sharing is paused. Why is my sharing paused? I don't like that window. I'm getting rid of it. Okay, but I can't see the thing again. And my computer's grinding. Okay, let me just see if I can get it up. There we go. Okay. All right. So I forgot what I was talking about. Did you have any more luck with just looking at integrals and so forth last night? Just sort of trying out things?
Yeah, I just took my time and I felt better about it.
Okay, good. Because what I can give you all the techniques and you can look in the book, but what it really takes is working at it and experience. And I can't give you experience. So you just keep working on it. We'll work some more at the end of class today. But what I want to talk about today is the beginning of chapter 10. And it's something called indeterminate forms. And what I want to do is start with a review from Calc 1, right from the beginning of Calc 1. Everybody look at that integral right there. Let me get my pen up. If you look at that integral right there, we remember from Calc 1 that the first thing we did was sort of try to plug something in and see if it worked. What happened with this problem when we try to plug 2 in?
It was a hole or something.
Denominator.
Okay, all right. Two things I heard that were right. That the denominator is 0 and also the numerator is 0. So if I just tried to plug something in, I'd get 0 over 0. That's called an indeterminate form, guys. When you get 0 over 0, and it didn't mean it didn't have a limit. And I think Alexis said something about a hole. So what this thing looks like, do you remember what we did to actually find the limit? Does anybody remember what we did to go past this fact that it was this indeterminate form?
No.
No? Do you see anything you could do to that fraction from algebra?
Oh, factor.
Yeah, that'll factor on it. And so this top one will factor into that, and this one will factor into that. That's a 2. It's a 2. And the x minus 2's go, and what I get is that the limit as x approaches x plus 2. So what happens is that it looks like a line. It looks like that line right there. That doesn't look very good, but anyway, it's an x plus 2 that's left. And if I graph that, it would be a line that looks something like that. But it's not defined at 2. The original function is not defined at 2, so there's a hole in the line. But if we now plug 2 into the part that's remaining, the x plus 2, we get the limit as x approaches 2 of x plus 2. And now we've sort of passed our problem. We'll get, that's not what we get. What do we get there, guys? What do we get? You get 4, yeah. So what's happening here is that the limit does exist, all right? It's just that the function doesn't exist there, but the value of the function is approaching 4 as we approach 2. So one of our techniques for doing this was to just, if we got this indeterminate form, it was just to factor it and hope that it's a hole in the function. If I ask you to do this one, if you plug in 3, the function's defined at 3, and it's a rational function. So if it's the denominator is defined, all we have to do is plug in 3. So if I plug in 3 to this one, it's going to be 9 minus 1, or 8 over 7, and that's the limit. In other words, there was no problem with that one. There was a problem with this one because of this indeterminate form. Okay, so if you go back, if anybody's got their Calc 1 test anywhere, guys, I got a phone call coming in I've got to take. I apologize. Take a break for a second. Debbie Harold.
Mama! Oh my gosh! Get her off of mute, Dion. Let me talk to your mama. I miss her.
Mom!
Dion, she won't let me come in her room.
I miss you.
No, I told Dion I wish she was quarantined with us.
Oh my gosh. I'm about to cry. Because I literally was thinking about you yesterday.
Huh?
I was thinking about you yesterday because I saw, the whole thing. Oh my God.
Hey, Alexis. No one invited you.
The whole family. Now, where's the older brother?
Oh, he's asleep talking to some
No, he's probably in there on the phone.
Oh, wake him up. Tell him to eat breakfast. It's morning time. It's
They
afternoon.
already ate breakfast and went back to their room.
Oh, see. I got up pretty late, I'm not gonna lie. I got up around like 10.
Okay, guys, I'm back. Sorry, that was from my dad's place. Okay. Boy, what were y'all yelling about?
I was talking to Dion's family.
Okay. All right, where were we? We were at these indeterminate forms here. And let's look at another one, guys. Right, on this one, if you plug in 0, you get 4 minus the square root of 16, which is 4 minus 4 over 0. That's another indeterminate form. So what happens is I get 0 over 0 again. Now, I know I got to do something to it. This 0 over 0 thing meant there's something you can do to it. And what we did to it in the previous problem was factor. This is not a factorable thing. So once we get that, we got to figure out what to do to it to be able to take a limit. Does anybody remember what we did with this one? I bet you it's almost like one I had on a test.
The conjugate?
Yeah, we multiplied by the conjugate. And it was the conjugate of this kind of messy thing right here. And so the conjugate of that would be 4 plus the square root of 16 plus x. And what you do in the denominator, you got to do in the, whoa, where'd it go? I keep touching it with my hand, and that's not good. What we needed to do then is multiply by the conjugate, both top and bottom. Okay. And then I'm not going to multiply that bottom out. I'm just going to kind of leave it like it is. And what'll happen in the top, if you look at the top, you'll get 4 times 4 will be 16. And so it's the limit as x approaches 0 of 16. The inner and the outer drop out because that's what a conjugate does. And then you'll get minus square root times the square root just gives you what's under there. So minus 16 plus x. All right, I didn't write that very well. 16 plus x. And remember, that's all over x times this thing right here. 4 plus the square root of 16 plus x. Now, the nice thing here is that this part right here, see that 16 and that minus 16, they're going to go. So those drop out, and I wind up with on top at least, I wind up with a minus x. Now, what's nice about that is that what happened? You got an x on the top now, and you got an x on the bottom. So what can we do with that? Yeah, you just divide them. It's just one in it, or it leaves you with a minus at least. So I'm going to run out of room here. So what happens here is, dang it, I did it again. I'm having trouble this morning. What I'm going to do is just write minus the limit as x approaches 0. And notice, guys, that it was that x being 0 that was causing a problem in both places. So it'll be minus 1 over this thing right here, 4 plus the square root of 16 plus x. I'm running off here. And now if I try to plug in 0, I get minus 1. That's really sloppy, but I get minus 1 over 4, 16 plus 0, and that's the square root of 16. So I get minus 1/8. Okay? So the actual answer in that one is minus 1/8. That's the way we would have done it in Calculus 1. Turns out there is a way to deal with these indeterminate forms that's pretty slick and easier than this. And it looks something like this. First of all, let's remind ourselves that 0 over 0 is an indeterminate form. There's one more indeterminate form. If you get something that's infinity over infinity, that's also indeterminate. Infinity over infinity is not 1. And it could be plus or minus infinity over infinity. It's something like, I don't know what that is. If you've got a function like this, then what happens is that if you let x go to infinity, what does e to the 3x do? I mean, if x gets bigger and bigger, e to a bigger and bigger power is going to do what? It's going to get, isn't it going to get bigger? I mean, because remember the exponential function is increasing. So what happens is that top's going to infinity. And how about x squared? You plug something bigger and bigger into x there, x squared is going to get bigger and bigger. So what we have is this indeterminate form called infinity over infinity. Now, we don't know how to deal with that one yet, but this thing I'm getting ready to teach you will help me deal with both of these forms. And it's something called L'Hopital's rule. Okay? And it's not hospital. I did not accidentally leave out an S. This is a French guy named, I can't remember what his first name is, L'Hopital. And he wrote a textbook, and it's in the 1700s or 1600s, I'm not sure when exactly. And this rule was in it. He did not actually discover the rule. It was his teacher that discovered the rule, but he got the credit for whatever that's worth. Here's what it says. And it gives me an easy way to deal with indeterminate forms that look like this. It says, suppose f and g are differentiable on an open interval containing c, except possibly at c. In other words, we might have a hole in the function there. If f of x over g of x has the indeterminate form 0 over 0 or infinity over infinity at x equals c, that is whatever you're approaching. And if g prime of x is not 0, in other words, the denominator is not, the g prime of x is not 0. We'll see why in a minute. For x not c, then this is true. It says, and it's an easy thing to use. It says the limit of that quotient is the same as the limit of its derivative of the top over the derivative of the bottom. Now that's not a quotient rule, guys. That's very different. It's just that here's time where you can take the derivative of the top, the derivative of the bottom. Provided either f prime of x exists over g of x, g prime of x exists, or it's going to infinity. So let me show you how that works, because it's really easy and nice in most situations. Let's look at the one that we did a minute ago, where we had to, remember this one right here? We had to factor that to find out right there, to find out what the limit was. What L'Hopital's rule says is, and I'm not going to take the time to prove it to you, but the proof is in the book. What L'Hopital's rule says is, if you take the derivative of the numerator, which is 2x, and the derivative of the denominator, which is 1, then the limit of that will be the same as, the limit of this will be the same as the limit of that. But that's easy to find the limit of. What do I do?
This first.
What?
Why didn't we do this first?
That's a good, well, I'll tell you why. Mathematically speaking, if the proof is in the book, you didn't have enough calculus to do the proof. So they leave it until this spot. They leave it until now, okay? So that, and it is easier. I mean, you just have to take the derivative of the numerator, derivative of the denominator, you get the value that we had. We get 4. Now, it's easy in that case, so we see that it works there. Let's see if it works on this one, because this one was really messy. We had to take the, remember we had to do the conjugate thing and I ran out of room, okay? So here's what I will do in this one. First of all, I check to see if it's an indeterminate form, and we already knew that we did get 0 over 0. Now, you always need to check, because if it's not 0 over 0, this is not going to work, or infinity over infinity. But what it says I'm going to do is I'm going to take the derivative of this. So the derivative of 4 is 0. The derivative of this, there'll be a minus there. This will be 16 plus x to the 1/2. So I'll bring down the 1/2, and it'll be minus a half. Take away 1, it'll be minus 1/2 up there. Derivative of the bottom is 1. So see what I did, guys? I just took the derivative of the top. I took the derivative of the bottom. Now I'm going to try plugging in 0. Nice thing about this, when I plug in 0, I get minus a half. I get 1 over the square root of 16. I get minus an eighth. Exactly what I got up here when I did it the hard way, which was multiplying it by conjugate. See, got minus an eighth. It was a lot easier. So this was a really nice advance in mathematics. All right, let's try another one that we don't know, but we know we might work. Okay, got stuff on my screen. All right, let's see if it's indeterminate. Now, I can tell you that in Calc 1, we would have no way to do this. Okay, we can't factor it. We can't multiply by conjugate. There's nothing that cancels out. I don't know what in the heck that thing's doing. I don't know what the function looks like, but I want to know what's happening as x goes to 0. If I plug in 0, and you really want to, you got to check, I'll have cosine of 0. Cosine of 0 plus 2 times 0, 2 times 0, minus 1. Ugh, my hand, I keep leaning on my screen today for some reason. Let's go back where I was here. And on the bottom, we would have 3 times 0. Notice the cosine of 0 is 1. So 1 minus 1, those cancel out. I get 0 over 0. Bingo. If I get that, I know I can use L'Hopital's rule on it. So let's go ahead and use L'Hopital's rule. That's the limit as x approaches 0. Now, we're going to take the derivative of this. So tell me what the derivative of the top is there, guys. What's derivative of cosine?
Negative sign.
Negative sign. The derivative of 2x is 2. And the derivative, I mean, put in 0 there and I'll just get, no, what's the derivative of 3x? I'm sorry, I said that wrong. What's the derivative of 3x?
3.
It's 3. Now, again, this is not the quotient rule. This is something we use, is something very different. But now we're going to try it again. So now if I plug in 0, I'll get minus the sine of 0 plus 2 over 3. And we know the sine of 0 is 0. So we get 2/3. That's the answer. That's the limit. Now, let's think about what a limit does again. And you say, well, how do I know it's the limit? One way you could do it is put this on a graph or put this on the calculator and look at the graph. And the closer you get to 0, the closer the y value gets to 2/3. If you traced it on the calculator, it would look like 0.66666. So as you approach 0, the value of the function is approaching 2/3. Easy to do with L'Hopital's rule. Really easy. I want you guys to do the next one. See what you come up with on that one right there. And first of all, verify that it's, well, let's verify it can be used for L'Hopital's rule to begin with. E to the 0 is 1. E to the minus 0 is 1. That's 2 minus 2 is 0. Cosine of 0 is 1. If I plug in 0 there, so 1 minus 1 is 0 over 0, and you're good to go. Use L'Hopital's rule on it, and tell me what the limit is. All right, let's see if everybody's differentiating right. What's the derivative in the numerator, guys? What's the derivative of e to the x?
E to the x.
E to the x. What's the derivative of e to the minus x?
Negative E to the x.
Negative e to the minus x.
Oh, yeah.
Because of the negative down there. And the derivative of minus 2 is 0.
Yeah.
This will be 1 minus the cosine. Whoops, sorry, messed up. What's the derivative of cosine 2x?
Sine 2x.
Derivative of cosine now will be
Negative.
actually minus sine 2x. And then I got to multiply by 2. What rule am I using there? Chain rule, yep. Okay. Now let me clean it up a little bit. Do not leave this limit off until you actually take the limit. So I'm going to get the limit as x approaches 0 of e to the x minus e to the minus x. This will be 1 minus 2 sine 2x. Oh, minus a minus, is that? Actually, it should have been it's a minus here. Minus a minus here is going to be a plus. Okay. Because the derivative of cosine, remember what gear you're in here. We're not integrating anymore, we're differentiating. So the derivative of cosine is minus sine 2x times 2. The minus that was already out here gives me the plus. All right, let's try again.
Is the 1 still supposed to be there?
That's
Shouldn't
a
it
good
be
point. It should be, what should be there, guys?
nothing?
If I'm taking the derivative, what should be there?
Nothing.
That should be it should be a 0, shouldn't it? I made that mistake on purpose. Right. Okay. All right. So we get that. All right, now let's look at it. Let's try it. What happens if I try to plug in 0 now? Plug in 0 to this, what do you get? 1. What do you get there?
1.
And 1 minus 1 is 0. What do you get when you plug in 0 and take the sine of 0? Unit circle sine of 0 is 0, because we're on the axis there. We get 0 over 0. So we use L'Hopital's rule, but we still got a 0 over 0. Guess what? I can use L'Hopital's rule as many times as I want until I get to something that either doesn't exist or is some number. So I'm going to do this again. I'm going to use, because it was an indeterminate form, the first time I use it, I'm able to use it again. So I'm going to write limit as x approaches 0. Okay, let's take the derivative again. E to the x. The derivative of minus e to the minus x will be plus e to the minus x. What's the derivative of 2 times 2 sine x? What's that going to be?
4 cosine 2x.
Okay, it's going to be 4 cosine 2x, because derivative of sine of 2x is cosine 2x times another 2. It'll be 4 cosine 2x. 4 cosine 2x. Now, this right here is the same problem. I have no idea why I wrote it down twice. I know what I was thinking. I was thinking I'm going to have to use L'Hopital's rule twice. Let's try again. So if I plug in 0 now, what do I get in the top?
4.
Well, e to the 0 plus e to the 0 will be 1 plus 1 will be 2. And down below, I do get what? What's the cosine of 0?
4.
1. The unit, where we are on the unit circle would be right here. Okay, so it's 1. So that limit is 2.
What about?
Right. Okay, does everybody see that? Oh, 2 times, and then 2 times what? The 4 to make it 1/2. I had the 4 down there too. So 4 cosine 0, which is 4 times 1. So I get 2 over 4 equal 1/2. So you can use L'Hopital's rule as many times as it applies, which is a really nice thing. Questions, anybody about that? Okay, see, this is pretty easy. Let's look at another one. Some things, though, you have to be kind of on your toes because you have to know what's happening for particular functions. And let's look at this one. I first need to know here for that function, if I approach pi over 2, what will tangent approach? Well, I drew the graph of tangent here, guys. You guys remember that from wherever, Math 25, high school, wherever. If you approach 2 from the left, remember how we had these asymptotes that tangent wasn't defined? If we approach pi/2 from the left, what's the function doing? Where's it going?
Infinity.
Infinity. So what I've got in this one, that one's going to infinity. Now, the tangent's pretty well known. The secant might not be something you have right in the top of your head, guys, but let me show you how I remember about what the secant is. The secant is 1 over what?
Sine.
Not sine, but
Cosine.
cosine. Okay? So 1 over the cosine. Oh, my pen is not right today. I'm messing up here. Oh, okay. So it's cosine. 1 over cosine. So here's what I do. If I want to remember what this thing looks like, I graph the cosine. And if I graph, because I know those are 2 things I always want to know what the graph looks like, the sine and the cosine. And if I graph the cosine, it starts up here at 1. It looks like, my pen is just doing bad today. Maybe it's me. It looks like that, okay? Now, it's got a period of 2 pi. It cuts the axis at pi/2. In other words, it's 0 at pi/2, and it's 0 at 3 pi/2. And here at pi, it drops down to -1. So that's what that would look like. If I went back another ways here, it would cut the axis again at minus pi/2. So guys, so why am I looking at tangent? Here's why I'm looking at tangent. I always have to do this to remember what secant looks like. Anywhere there is a 0, like right here, if the cosine is 0, what can you say about the tangent? I mean the secant. If the cosine is 0, right there at pi/2 and minus pi/2, what can you say about the secant?
Undefined.
It's undefined. Because you can't have a 0 in the denominator, and it's undefined in the same way the tangent is, because tangent is sine over cosine. The problem was that the cosine was 0 at those places. So what I've got in those spots, anywhere the cosine crosses the axis, I've got an asymptote. Okay? So I've got this asymptote there. Now, those are asymptotes for secant. And notice here that the secant is just the flip of cosine. So for example, if the cosine was 1, the secant would be 1. But if the cosine was 1/2, the secant would be 2. All that does in the graph is flip it. All right, it flips it. If you went further down here, it would flip it right there. There'd be another asymptote right there. That's how I draw the secant. But here's what I want you to see. As we approach pi/2 from the left, what's the secant doing? That's what it looks like. What's it doing?
Infinity.
It's going up to infinity. So what I've got here is an infinity over infinity form. So that tells me I can use L'Hopital's rule on it. So that's going to be nice. So sometimes you got to know what the graph looks like, guys. You can't if you plug in pi/2 to tangent, you're going to get you can't, because it's undefined there. All right, so here's what I'm going to do next. I'm going to apply L'Hopital's rule to the thing. And L'Hopital's rule says this limit right here is going to be the limit as x approaches pi/2 from the left. What's the derivative of the top, guys? What's the derivative of 4 tangent x? Anybody?
4 secant squared.
Yep, 4 secant squared over 1, sorry, jumped the gun. What's the derivative of 1? 0. What's the derivative of secant?
Secant tangent.
Secant tangent. Okay, so that's good. So that's going to be secant tangent. Now, we're going to simplify it. And with trig, you know, there's a lot of options for simplification, but I see one way to simplify something quickly. What do you see quickly I can simplify there, guys?
It'll be 4 secant x on top.
Yep, because that's going to go with one of those. All right. So, but we still have, look at this. We got a little problem here, because when I write that, its limit as x approaches pi over 2 from the left. And that'll be just a 4 secant x over tangent x. But I got the same problem, because as we approach pi over 2, that's going to infinity, and that's going to infinity. But don't use it again. Don't use it again yet. You might be able to use it, but I think I can simplify this and make my life easier here. If you were doing trig identities, what's a way you might think to rewrite that thing right there?
1 over cosine and sine over cosine.
All right, I like that. So let's write this like this. The limit as x approaches pi over 2 from the left. This is going to be 4 over cosine. This will be sine over cosine. I'll get rid of this in a minute. When I invert and multiply, I'll get the limit as x approaches pi over 2. Invert and multiply, I'll get 4 over sine. Okay, I like the looks of that better. And guys, if I had used L'Hopital's rule from here, it would have just started getting messier. If you find your function getting messier, particularly with trig functions, see if there's some way to rewrite it. Okay, here's the question. Can I do this? What's the limit as x approaches pi over 2 from the left of 4 over sine x? Well, what's the sine of pi over 2? And by the way, it doesn't matter if it's coming from the left or the right, because sine is continuous there. So what happens? What's the sine of pi over 2?
1.
Yeah, up on the remember up on the unit circle, on the top of the unit circle there, the y value is 1. So the answer is 4 over 1, and that's the problem. Okay. On the trig ones, you do have to know, you have to use, and you guys, you can use your unit circle now. We sort of all resources are available that we've had before, so you know what you can do with that. Okay. So I used L'Hopital's rule in a form that was infinity over infinity. All right, let's try another one. And I kind of got in my way down here, but we'll do another one here. I'm gonna draw a line here, so we know what happened. Okay, let's see what happens with this. You got to determine whether it's a L'Hopital's rule problem. I want you to remember for me what the log looks like, because this is another one where it's going to help us to know what the log looks like here. What's the natural log of x look like? Don't go to your calculators. This is when you need to store.
Is reflected over y equal x or x equal?
It's sort of, yeah, that you're thinking about, it's an inverse of an exponential function. So if the exponential function ran right here through 0, 1, the log is going to run right here through 1, 0. So that's what that looks like right there. So it goes 1, 0. Okay. So tell me what the log of x is doing as x goes to infinity here, guys. What's the log x doing?
Going to infinity.
Going to infinity. It just keeps on increasing. If you take its derivative and you look at its domain, the derivative is always positive. That means it's always increasing. All this stuff we learned from Calculus 1. So that right now, we're looking at this, that this is infinity in the top. Okay, what's the square root of x do as x gets bigger and bigger? Plug in a bigger and bigger number, what happens to its square root?
Bigger.
How about the square root of 10, square root of 100, square root of 500? It's getting bigger and bigger, isn't it? You take a square root of a bigger number, you're going to get a bigger number. And you might want to think about it again as a graph. The square root of x looks like that. All right, the square root of 0 is 0. Square root of 4 is 2. Square root of 9 is 3. It's getting bigger. So we've got infinity over infinity here. Okay? So I can use L'Hopital's rule now. And here's what I'm going to do then. What's the derivative of the log of x? Guys, I'm going to take the derivative of the top. What's the derivative of that?
1 over x.
1 over x. And then I'm going to take the derivative of the bottom, which is 1/2 x to the minus 1/2. All right. I'm going to get rid of one of these so I can y'all can remember what square root of x looks like, so I have a little room here. All right, everybody see what I did? I just took the derivative of the top, derivative of the bottom. Now, it's kind of ugly. I really do need to clean this up a little bit. So you want to stop along the way and simplify. It'll make your life easier. The limit as x approaches infinity, this will be 1 over x. And when I invert and multiply, there'll be actually a 2 there. And x to the minus 1/2 will come up as x to the 1/2 up there. Okay, so everybody, I'm getting low on the screen here. Look at what I did. The 1/2, that came up as 2 over x. And this is 1 over x to the 1/2, so it ended up looking like that. Okay. So now, is there anything else I can do to simplify that, guys?
The x's.
Yeah, let's combine those two things. If I've got limit as x goes to infinity, that's 2. 1/2 minus 1 will be minus 1/2. If I drop it into the denominator, it'll be 2 over square root of x. So here's the simplification. X approaches infinity of 2x to the minus 1/2. Drop it, and it'll become that. Okay, now, I want to talk about two things here. If x is going to infinity, what's 2 doing? What's the limit of any constant? It's just 2, right? It's not going anywhere, is it? It's just because there's no x there. What did we say the square root of x was doing? It's getting bigger and bigger. It's getting bigger and bigger. So if the numerators stay the same and the denominator is getting bigger and bigger, where is this thing going?
0.
0. So for instance, if I had 2 over 10, 2 over 100, 2 over 1,000, that thing's going to equal 0. Now, let me, does everybody see that? 2's stuck. This is getting bigger and bigger. It's in the denominator. You're getting a smaller and smaller fraction. That's all that's happening. This is why infinity over infinity works here. Because if you really looked at these as 2 functions, it just means this function right here, 2x to the 1/2, is growing slower than x. And eventually it goes to 0. That's what L'Hopital's rule allows you to see, which is really pretty nice. So first step, make sure you can use L'Hopital's rule with either 0 over 0 or infinity over infinity. Take the derivative of the numerator and the denominator, simplify with Triggs functions or other functions, and then just resimplify and take the limit. Everybody okay with that one? Let's do one more here. I think I've just got one more. Yeah, I do. Okay, so let's see if we can use L'Hopital's rule on this thing. If you plug in 0, you get e to the 0 in the top plus e to the minus 0, which would be 1 plus 1, which would be 2. Okay? And then what would I get in the bottom if I plugged in 0 to the bottom? I get a 0, right? Guys, that doesn't give me anything I can use L'Hopital's rule on, but it does give me a hint about what it is. You remember in Calc 1 where we said we got a constant in the top and a 0 in the bottom? That meant the bottom was getting closer and closer to 0. So it was either shooting up to infinity or shooting down to infinity. In other words, it's getting bigger and bigger. It's going to a smaller and smaller fraction. So for instance, if I put 1/10 in here, would be squared would be 1/100th. When I inverted and multiplied, I get 200. If I put 1/100th, I'm getting closer to 0. That thing squared would be 1 over 10,000. Invert and multiply would be 10,000 times 2. Remember when we used those tables and we looked to see what happened? This thing, when you get that thing right there, it's either shooting off to infinity or minus infinity. Because that's a square and it's always positive, where do you think this one is going? That's 2, and that's always positive, getting bigger, getting smaller and smaller. It's going to, they're also always positive, right? So what's happening here is this thing is going to infinity. Because that denominator is getting smaller and smaller, and 2 is stuck. The limit of 2 is 2. So we're done with that. That's an example where you don't want to use L'Hopital's rule because you'll come out with the wrong answer if you use L'Hopital's rule. You got to always check. Always check. Okay? And particularly when you get this form, you're going to have something either going to infinity or minus infinity. If I'd had a minus right here, it would have been going to minus infinity. But doesn't matter. It still doesn't exist. Okay. I think that'll lighten up a little bit the homework. I've put on your assignment sheet. Well, down here is the homework too, but it's also on the assignment sheet. Let's see. Come on. Down here is the homework, so it's just a few of those things to do. And you know, I've got 1 through 29 odd. It gives you a lot of practice. If you don't have a lot of time, I think you get plenty of practice here if you did maybe every other odd. Okay, but because it's not hard, it's not a hard thing to do, but that's, you know, that might help if you're stuck at the end of the week. Okay, so that's all I want to do for L'Hopital's rule today. Does anybody have any leftover intervals you want to look at? Things you were having trouble with from last night? Who's scraping something? What is that? I couldn't hear it. Is that you, Alexis? What are you doing?
That is not me at all.
Okay, sorry. I don't know. You were looking down. I was thinking you were scraping something off the desk.
Funny.
Okay. Anybody got an integral you want to look at that you didn't know what to do with, or we didn't do yesterday? Things you might want to look at. You know I'm gonna give you one if you don't give me one. What if, and we did most of those yesterday. You know, this is where cutting pages out of your book doesn't work too good because I don't have one. Somebody take your book and who's got their book with them? Got their book beside them. Okay, Lexus, open that book to that page where there were those 100 integrals. Okay. And pick one. I just want you to pick one. So I want everybody to just sort of guess what's going on in that integral. Pick one and let's see what's happening.
I want to pick 67.
All right. Tell me what 67 says.
I guess the integral of x squared minus like SECH.
Oh, guys, there were 2 that I eliminated there. This thing, SECH, is called the hyperbolic secant. We did not do that section. So if you see something that looks like a trig function with an H after it, I eliminated it, okay? So I think
what it was like.
If you look on the original sheet, I think I said except those 2. I said I don't want to do those because we don't know how to work with them, okay? They're actually easy, but not. Pick another one. Pick another one.
I'm gonna choose 94.
94?
Yeah.
All right, hang on. Wait a minute. Let me get my screen clear here. 94. All right, what do you got?
Cotangent squared of x, cosecant x dx. It's just an integral. Yeah.
Okay. So that was 90 something. What was it, 90?
It's not square. It's just cosecant x.
Oh, it's just cosecant x? Okay.
Yeah, this 94.
That one? Okay, 94. So that's what section do you think this comes from, guys?
9.2.
Yeah, it looks a lot like 9.2. By the way, I've got your stuff in. I think everybody sent it to me, but I'll get it back to you. I may have to wait till the weekend to catch up with my grading. I graded a long time yesterday. What do you think I could do with this one? Now remember, you're trying to create a U and a DU. Think about what you know the derivatives of and what you got right there. I heard somebody start to say something.
That was Tierra.
I was gonna say you could split off a cotangent because cosecant and cotangent are the derivative of cosecant.
Okay,
Question mark.
I think you got, we'll look at it. I think you got a good idea here. So she split off a cotangent and was left with another cotangent. So what's the derivative? Can we make something out of that? What is the derivative of cotangent, guys? What's the derivative of cotangent?
Negative cosecant squared.
Yeah, it's negative cosecant squared. I don't see that there. If there had been a square on this one instead, that might have worked.
Yeah.
What's the derivative of cosecant?
Negative.
Yeah, negative.
Okay. Cotangent, cosecant.
Right. So if I let that be u, I don't have what I need for its derivative either. That's a good one because you know it doesn't quite fit. But let's think about it. Do I have any identities I might use on this thing, guys?
1 plus cotangent squared.
I've got the 1 plus cotangent squared equal cosecant squared. And I don't have a cosecant squared, but I got a cotangent squared. If I put a cosecant up there,
So can we replace it with cosecant squared minus 1?
yeah,
no?
let's just try it. We'll see if it works. Okay, so I'm going to have this one right here would be cosecant squared x minus 1 times cosecant x dx. All right, I kind of like that idea because if I multiply it out, minus cosecant x, I at least have one thing I can integrate because I know the integral of that. This one, makes that cosecant cubed right there. This one is harder. And I remember I showed you the other day, I told you that secant cubed was kind of hard, and I said it was example 6 and 9.2 or something, and you had to split it and use parts. Cosecant cubed is like that. You have to use parts. You have to split off a cosecant squared and have a cosecant left. I'm thinking, but you know, if I was really thinking, well, I could do that if I wanted to, but would there be anything else up here you might be able to do that might make it look different and helpful? Can you change code? This was always my chicken way out when I was trying to show identities. I'd say, well, I don't want to deal with cotangents and cosecants. I'm going to change everything to sine and cosine. And I don't know if it's going to work, but let's look at it, okay? You could do this one, but you have to go back to that section. You have to peel off a cosecant and make it a parts problem. So it's pretty messy. Okay, so here's what I'm going to do. I'm going to change this to sines and cosines. What's the cotangent in terms of sines and cosines?
Cosine over sine.
Cosine squared of x over what? Sine squared of x?
Yeah.
And this one's 1 over
Sine.
sine of x. I don't like that either. Okay. So that's going to be, well, let's see. I'm kind of not liking this, but let me try something else. So I'll have cosine squared over sine x cubed. I'm going to persist. Don't know where I'm going. Truly, I don't know what I'm doing here. And that'll be 1 minus sine squared. And that'll be sine cubed. Boy, this is getting worse and worse. Because 1 over sine cubed, that ain't going to help me any. I might be able to do this piece because that's just 1 over sine, which is cosecant, but I'm still in the same mess I was before. Look, it's exactly the same thing because that's minus 1 over sine would be cosecant.
Why did I choose this one?
And this would be you chose it. Okay.
I'm like, why did I do this?
I don't know because this is a harder one, guys. This one you can do that. That one you can use parts on. And look back in that 9.2 section and you'll see how to use parts. That's a hard one. That's a hard one because it's not easy. Just when you split off one piece like we did to begin with, nothing worked out. So it's not a
if we were to do it by parts, what would we make?
Here's what it would look like if you did it by parts. Just roughly to begin with. I would say let V, this part right here, guys, because this one you know. Let V equal cosecant squared x, because that dV is easy. What's dV there, guys? Whose derivative is cosecant squared?
I mean, cotangent.
Minus cotangent. Good. That leaves my du as another cosecant, the other cosecant. So, sorry, it's just the cosecant. Okay. So the du is cosecant. So what's u? You would have to, this is not pretty, but what's the integral of cosecant? That doesn't look very good there. What's the integral of cosecant x? This is dx. Remember, that's one of those log things, isn't it? Remember? This was ugly, okay? Do you remember what it is? Do you remember what, if that's du? I'm sorry, that u dv.
Oh, wait, yeah. The natural log of sine.
Yeah.
No.
What?
I don't know.
I let my, here's what I did. I did something wrong, guys. Hang on a second. See, I kind of play around with it too. Let me say something here. Usually what I pick when I'm doing parts is u and dv. U and dv. What I want dv to be is the cosecant square. Okay, I want that to be the cosecant squared. I had it kind of written backwards. Cosecant squared x dx, and then v would be cotangent, minus cotangent. I want u to be the other cosecant. There we go. That's what I want. So u dv. So tell me what du will be. That's kind of easy at this point. Tell me what du would be. What's the derivative of cosecant?
Negative cosecant cotangent x.
Yeah, negative cosecant cotangent. So negative cosecant x cotangent x. Now, that's how I would set it up with parts. That means then that uv cosecant x times minus cotangent x minus the integral of v minus a minus cotangent will be cotangent x. That's v du. I go back to a minus because it's going to be minus cosecant x cotangent x. Now, here's something that we talked about earlier. You may not remember it, but darn it, it's looking sort of like it did right in the beginning, isn't it? What you do, remember, is take that over to the other side, and there'll be two of them, and then you can work it out. Because if you look at that one, it's cotangent squared cosecant x. If you go back, it's cotangent squared cosecant x. It's the same thing I was trying to integrate up there. I'm not exactly going around in a circle because there's a minus here. This whole thing right here will be a minus. And now you can take it over to the other side and you can say there are two of those and it's equal to that. Think about it, okay? It comes right back to you, but it comes back to you with a different sign. Boy, you picked a hard one.
Yeah, don't have me choose questions because I just chose that one because, you know.
I know. Well, initially it looks like it'll be easy, but what makes it hard is that there's a cube on here. That really makes it hard. And again, it's back in that 9.2. There's one. If you look at secant cubed, you'll see what they did there. Okay, I'm done, guys. Unless anybody wants to hang around and ask me any homework questions, but work on L'Hopital's rule tonight. Pretty easy, okay? And I'll answer questions about that tomorrow. So what your next test will consist of, I've got a little more to say about L'Hopital's rule.
Wait, when is the test?
I don't know. We hadn't decided. Y'all talk. You want to talk to me now? Or you want to talk to me tomorrow? I don't care.
You got me scared for a second. I was like, dang.
I'm going to give you I'm gonna get, it'll be like 10 or 12 integrals to do, and I'll get you to pick your favorite 10 or something, and then it'll be some L'Hopital's rule problems. That's what the test will be. And we will take the day off, the day y'all have a test. So we won't meet class that day. So you'll have, I'll probably post the test. Say if we have it on Wednesday, I'll post the test on Tuesday and it'll be due Thursday morning. Something like that. So I'll give you a little time. But you were telling me you had extra stuff to do towards the end of the week. You didn't want to do it over the weekend. Is that true?
Yeah, I don't want to do it on the weekend.
Okay. Well, we'll be through with this tomorrow.
I guess the days you said was fine. Like, I'm fine with the Tuesday.
Well,
I don't have any classes on Tuesday, like except for math.
okay. Well, I tell you what, y'all think about it. I'll be through with what I want to do on this and what I want to put on the test. Most likely tomorrow. We'll use Monday to go over anything, problems left over with L'Hopital's rule and any problems with the integrals. And then I'll post it. If you want to do it Tuesday, whenever, I'll post it, give you the next day completely off, and it won't be due till the next day after that. We will have class the day it's due, okay? So that should give you plenty of time to work on it. Because as I said, with some of these integrals, sometimes you're going to want to walk away from them and say, I'm gonna let that one sit for a minute and see if something comes to me, okay? And I think that'll give you plenty of time to do that. So y'all think about it. It could be, I could give it to you Monday and have it due Wednesday, or I could give it to you Tuesday and have it due Thursday. I'll talk to you tomorrow about it, okay? Consider what you want to do, and we'll go from there, okay? So it'll be next week, first half of next week. All right, are we done?
Yep.
Anybody else want to chat with me about anything? I'll see you tomorrow then. Bye.
Like,